Imagine building a structure as tall as a 100-story skyscraper. Build it on its side. Pull it onto a barge. Tow it through narrow, winding waterways. Launch it in the open sea in water 1,000 feet deep. Build it so that this massive structure floats. Rotate it to upright and set it on the sea floor. Top it with another 30 stories, then use it to drill for oil. Much of what we do or have depends on oil or its byproducts. The world uses more than 50 million barrels of oil a day for transportation, heating, chemicals, food, and much more. Where do these byproducts come from? They begin here. Crude oil, formed beneath the Earth's surface over millions of years. Producing the oil is tough, hard work and expensive. When new oil is found, new technology is often needed to produce it. This is especially true in offshore production. Today, platforms can be as tall as skyscrapers. The largest are almost 1,300 feet tall and can weigh 50,000 tons. Bringing oil from beneath the ocean floor is a remarkable story of daring and innovation. Men work long hours, round the clock, in often hostile environments. These steel giants must stand against nature. The fury of hurricanes, earthquakes, subsea mudslides, corrosive salt water, and tremendous pressure are constant concerns for developing offshore fields. The equipment loads placed on them, vibrating compressors, drilling rigs, and strings of pipe that when coupled can be more than 5 miles long, are tremendous. Not long ago, man crossed the technological barrier from land wells to offshore production. In 1947, the first platform was installed in 20 feet of water. Exploration continued. New technology developed. And within 20 years, platforms were standing in 300 feet of water, a major plateau. Going deeper would require overcoming obstacles. Simply scaling up smaller structures no longer worked. New forces come into play. The relatively long, slender platform was bending and moving with the current. Exploration moved further offshore into new frontiers, and marine construction technology kept pace. Record-breaking water depths were realized as platforms stood in nearly 500 feet of water. Platforms were getting bigger, taller, heavier. In order to install these steel islands, the industry had to develop equipment to handle the job. Modified material barges with cranes were first used. Today, a virtual navy of specialized vessels has evolved. These, along with pipe laying, launch, and material barges, make offshore construction possible. In 1976, offshore construction achieved another technological leap. This platform, called Hondo, is a multi-section jacket installed in 850 feet of water. Its installation method was unique and provided one solution to deep water production. Existing launch barge equipment could not transport a structure this big in one piece. The solution? Build Hondo in one piece, cut it in two. Load the first section onto a specially built barge, tow it out to sea, and launch it. Then send the barge back to carry the second section to location. While the two sections are still floating horizontally, rejoin them. Welders work below the surface, inside the hollow legs, to form a single jacket. When welding is complete, upend the structure on location and pin it to the sea floor. While Hondo was still under construction, the industry did not stand still. A platform requiring even greater innovation was begun. Cognac, the tallest and most complex offshore structure yet built, stands in the Gulf of Mexico in more than 1,000 feet of water. From the beginning, engineers knew the project would be filled with difficulties. Because of its weight, Cognac was built and installed in three pieces, which must fit perfectly, as they will be mated underwater. The base, because of its width, more than a city block, must be fabricated upright. It is built and installed more than a year before the other sections. A trial fit is impossible, yet tolerances are critical. A laser measuring device assures precise measurements. The middle and top sections, each one far larger than a conventional platform, are fabricated, loaded out, towed separately, and prepared for the most complex installation ever attempted. Acoustic beacons pinpoint the precise position of each section as it is lowered and mated to its predecessor. Television monitors enable engineers to oversee the underwater operations. Divers breathing helium and oxygen work at record depths. Cognac's fabrication and installation took more than 3 years. During this time, energy demand continued to increase. New reserves would have to be developed, and still deeper water would be encountered. The challenge is to build and install a 1,000-foot jacket in a more economical manner. In the past, one-piece structures were the standard of the industry. Their engineering concepts and designs were proven and provided the basis for cerveza. Engineering for fabricating and installing an almost 1,000-foot platform in one piece went from a concept to a reality. The challenge of building and installing a jacket this big required careful planning and execution. The entire contract is performed under the guidance and expertise of one major contractor. The company commits to build the world's largest launch barge, one big enough to carry the new jacket on its deck. The jacket must be ready to launch 18 months after the project starts. Meeting the deadline requires a precisely coordinated effort. The one-piece engineering concepts and designs have been proved in shallower water. Adapting them to deep water proves not to be a straightforward change. Because launch is the key to the project, engineers begin with launch analysis data for a 952-foot platform. The analysis, a conventional type used on smaller structures, shows platform members so heavy that the structure cannot be moved. Weight, once again, haunts the efforts of the designers. Engineers turn to a new procedure, dynamic analysis. This method accurately predicts the stress on each member of the jacket. Engineers can use less steel, which means less weight. The interaction of barge and jacket, a key element during tow and launch, is simulated by computer and by use of scale models. The data give engineers an exceptionally accurate account of what will happen during the actual launch. The design will work. Construction begins as close coordination between engineering and the fabrication yard sets in motion a system called fast tracking. Drawings are completed in fabrication sequence and sent immediately to the yard. Modern auto-drafting machines, along with conventional drawing methods, produce the hundreds of drawings needed to execute a project of this magnitude.
All right, come up a little bit. All right, come on. A little bit more. Oh, right there. Now what you got?
Survey crews, welders, dozer operators, riggers, and project supervisors work together to build the jacket. Because working on the ground is safer, faster, and more comfortable than working high in the air, schedules are organized so that most work can be done while the leg sections are on the ground. Outfitting, that is, adding hydraulic lines, anodes, flood valves, everything that can be, is done before the leg sections, called bents, are raised. Because of their extreme length, the bents are built in two sections. Each section is rolled up separately by a team of cranes. The scene is set for the first of 9 major roll-ups as the structure begins to take shape. The bents are rolled and welded, a choreography of men, machines, and steel. The activity and Cerveza grow. Intermac 650 becomes part of the scene. The world's largest launch barge, the 650 can transport 40,000 tons, equal to over 20,000 full-size automobiles. It, like Cerveza, is an important link in the future of deep-water technology. The completed Cerveza is 952 feet long, with a launch weight of 26,000 tons. 18 months after the project began, the structure is ready for its sea journey. The Intermac 650 is positioned and loadout started. Ballasting is critical. The barge has to be level with the dock. So as the tide moves and as more of the jacket's weight rests on the barge, ballasting adjustments must be continual. Hydraulic jacks pull the structure from the dock. A slow, tedious move from the stability of land to a floating vessel, dwarfed by this mammoth structure. The task requires more than 22 hours. Cerveza is secured and made ready for tow to location. The trip through the bayous of South Louisiana lies ahead. Additional preparations are needed before the long tow begins. Tugboats arrive. The bayou is closed to all marine traffic and the weather conditions monitored closely. The go-ahead is given, and slowly the structure is turned. Two pulling tugs and one of the world's largest push boats move the structure through the narrow waterway. After 2 days, the tow moves into the Gulf and continues on to location, 90 miles south of Freeport, Texas. Good weather continues, and the barge is moved into position for launch. Supports are cut. The barge is ballasted toward the stern. Hydraulic jacks are charged, preparatory to moving the jacket. Tugs are positioned, and a final inspection completed. The go-ahead is given, and the jacks begin to push. Slowly, the giant structure begins to move on its own. She floats as calculated. Controlled flooding of the jacket members rotates the structure to an upright position. In water deeper than its final resting place, it is leveled, then towed to location and set on the bottom. The installation of 16 skirt piles and 8 leg piles, in all several miles of steel piling, pin Cerveza to the floor of the Gulf. Arriving late in the afternoon, the deck sections are lifted and set at night. Later, drill packages are positioned. Painting, electrical connections, and general startup work is performed to complete the platform. The offshore installations take less than 3 months. Drilling is underway. The project is completed 1 month ahead of schedule. Like the early platforms that ushered in the industry offshore, Cerveza, Cognac, and Hondo are the giants upon whose shoulders the next generation of deepwater platforms will stand. The future of deepwater production will depend upon the advancement of new technology. Larger fixed platforms, along with tension leg and guide tower structures, are just beyond the horizon. Current technology allows us to combine large single-piece structures, making 1,800-foot water depths accessible. New construction methods may be simple or they may be complex. None will go without risks. Whatever the solution, dedicated men and women will meet the challenge. They will confront tomorrow's energy problems with efficient, practical solutions.